So given here is the solution to the first assessment questions, the numerical questions that were asked, and starting with question 1. So in question 1 it was asked to find the voltage across a 5 ohm resistor, and this was to be done using Thevenin's theorem. So if you look into the figure where 5 ohm resistor is given in between the two branches of 10 ohm and 15 ohm. So as we learned that in order to find the Thevenin's equivalent circuit, we will first obtain the RTH, that is Thevenin's equivalent resistance, by removing this resistor and open circuiting the current sources and short circuiting the voltage sources. So after obtaining this circuit, we will be finding the resistance values across these two terminals, which will be RTH, and this can be obtained by, because this terminal which is open now is useless and can be removed. So what we are left with is 10 ohm in parallel with 15 ohm resistance. So the parallel combination of these two resistances gives us 6 ohm resistance as RTH. And the next step is to find the Thevenin's equivalent voltage. So for that, what we do is we reconnect all the sources that were open circuited or short circuited back to the circuit, and then we perform the analysis using whatever techniques we know. For example, I have done this using KCL and KVL. So the 2 ampere current that flows in this branch, and we assume I1 to be flowing in this branch, and then apply KCL to this node, gives us 2 minus I1 at this branch, and we apply KVL to the loop, to this loop, and what we get is 15 I1 minus we move anti-clockwise while applying KVL to this loop. So this gives us 15 I1 minus 10 into 2 minus I1 minus 12 equal to 0. Solving this gives us I1 equal to 1.28 amperes, and from this we can obtain VTH, that is the voltage which would be appearing across these two open terminals, and this will be equal to the voltage that appears across the 15 ohm resistance, and thus 15 multiplied by 1.28, the current that flows through the 15 ohm resistance, gives us 19.2 volts, Thevenin's equivalent voltage. Now to obtain current that the Thevenin's equivalent circuit is shown on the bottom left side, where we have the voltage source connected in series with RTH, and we reconnect the 5 ohm resistance, which was the resistance under consideration. So we get this Thevenin's equivalent voltage, and from this we obtain current as I equal to 19.2, this value, divided by total resistance 6 plus 5, this gives us 1.74 amperes, and thus the voltage that appears across 5 ohm resistor would be the current multiplied by 5, which gives us 8.73 volts. As for the Norton's, the question 1 prime, where the circuit was supposed to be solved using Norton's theorem. So in order to obtain Norton's resistance, the same steps are applied that are applied for Thevenin's equivalent resistance, and we are going to open circuit the current source, short circuit the voltage sources, and then we'll be finding the Norton's resistance after removing the resistance under consideration. So we obtain Rn as 2 ohms. Now to find Norton's equivalent current, what we do is we reconnect all the sources back to the circuit, and the terminals where this 2 ohm resistor was removed is short circuited now, and we are now going to find the current that flows through this short circuit, which will be giving us In. So if we apply KVL to this loop, what we get is 2 minus In plus 10 minus In equal to 0. So 0 had been left out here, so let me write this. So this should be 0, and solving this gives us 2 In equal to 12, or In equal to 6 amperes. So now we draw the Norton's equivalent circuit, which is In equal to 6 ampere connected in parallel to the Norton's equivalent resistance 2 ampere, and then we reconnect the resistor that was initially removed back to the circuit. So this gives us, if we apply current divider rule, so this is current divider rule, this gives us I prime, which we assumed as the current that flows through the 2 ohm resistor. So I prime is In into 2 divided by 2 plus 2, which is 3 amperes. Voltage across 2 ohm resistor is now 3 into 2, that is 6 volts. In the next question, in the second question, we were required to find the current that is drawn by the circuit, and we are also required to draw the waveforms of current and supply voltage. So if you look into this circuit, we have three impedances. So one for two impedances are corresponding to the two parallel branches, and then the third impedance is connected in series to these two parallel combination. So to find the equivalent impedance of this circuit, that is Z, which is nothing but the Z3, the impedance which is connected in series, which will be added, because as I told you that impedances when connected in series are simply added, and when they are connected in parallel, they are then the same formula applies as we used to apply for resistances. So this is the series branch. Then we have two parallel branches which are connected in parallel, so we obtain their parallel combination. So then the calculations are given as follows. Since we have this has inductor 0.2 Henry, and this was capacitance of 400 microfarad. So for this we have j xl, and this is minus j xc, where xl is omega l and xc is 1 upon omega c. So we further simplify this, and we in fact will be using polar to rectangular conversions to solve this problem. So we have converted this to polar form here, then again this to polar form, so that multiplications could be done easily, and then we simplify this to obtain 0.98 minus j 0.76, which is the parallel combination of the two impedances. Then this is added to the series branch, and since series branch we have converted this into polar form, then we now, because we are going to add them, so we'll have to convert this back to rectangular form. So 10 plus j 5 pi will be added to this, and this gives us the equivalent impedance in ohms. So this is in ohms. And to find the current that flows through into the circuit, we simply divide the voltage supply, which is 220 angle 0, divide by the impedance, the equivalent impedance that we just obtained. So this gives us the current as 11.83 minus 53.9 degrees ampere in polar form. So this is the required current that is required to be calculated. Now to obtain the waveform for this, so we'll refer to the phasor diagram. So V 220 angle 0 will be taken as reference, and we obtain current as 11.83 angle minus 53.9. So the phasor for this will be corresponding, will be lagging voltage by an angle of 53.9 degrees. And for waveform, since voltage is the reference value, the reference wave, so this will be starting from 0. And for current, we have it as lagging current, so similar to what we studied in purely resistive, purely inductive, and purely capacitive circuit, that which quantity is going to lag which one. So applying the same concept here, so 53.9 degrees lagging means that the current will be starting 53.9 degrees after the start of the voltage, and their maximum, the peak values are written as 220 root 2, because 220 is the RMS value, and 11.83 which had been computed using the RMS voltage is also the RMS value of the current. So the peak value can be obtained simply by multiplying them with root 2. And then the remaining questions corresponding to question 3 are related to theory and derivation, so that can be referred to the class notes.